In this lesson, we're going to look at two important EAS reactions, the Friedel-Crafts alkylation and Friedel-Crafts acylation. The Friedel-Crafts alkylation replaces a hydrogen atom on a benzene with an alkyl group. As you can see in the example, the reaction is usually performed with one equivalent of an alkyl halide in the presence of a Lewis acid, typically aluminum chloride. In most cases, the alkyl group attached to the halogen replaces a hydrogen on the benzene. The Friedel-Crafts alkylation is synthetically very useful because it makes a carbon-carbon bond. One issue with the Friedel-Crafts alkylation is that most primary alkyl halides result in rearrangement of the alkyl group. In this example, we see the reaction performs with 1-chloropropane. The expected propylbenzene is only formed as a minor product. The major product is the result of a rearrangement, in which the benzene attacks a more highly substituted carbon adjacent to the halogen. Mechanistically, the Friedel-Crafts alkylation is an electrophilic aromatic substitution, at least when viewed from the perspective of the benzene. However, the benzene is not the only organic molecule involved in the reaction. From the perspective of the alkyl halide, the Friedel-Crafts alkylation is a nucleophilic substitution, and the mechanism can occur via either SN1 or SN2, depending mostly on the structure of the alkyl halide. So let's take a look at the actual mechanism. As with all EAS reactions, the first step is the formation of a powerful electrophile. In this case, the electrophile is formed via a simple Lewis acid-base reaction. The alkyl halide acts as a Lewis base. The halogen donates a lone pair into an empty orbital on the metal of the Lewis acid catalyst. The resulting adduct serves as the electrophile in the EAS reaction. In this example, I've chosen to use a secondary alkyl halide. You might recall that secondary alkyl halides are prone to both SN1 and SN2 nucleophilic substitutions. In the SN2 version of the reaction, the benzene attacks the electron-deficient carbon of the electrophile, breaking the carbon-chlorine bond in a single step. The resulting resonance-stabilized carbocation is then deprotonated by a weak base, reforming the pi bond and re-establishing aromaticity. In the SN1 version of the reaction, the electrophile dissociates, forming a carbocation. The carbocation is then attacked by benzene to form a carbon-carbon bond. Just as before, the resonance-stabilized carbocation is then deprotonated by a weak base, forming a new pi bond and re-establishing aromaticity. Typically, methyl and primary alkyl halides go through the SN2 reaction mechanism, whereas tertiary alkyl halides go through the SN1 mechanism. Our last EAS reaction is the Friedel-Crafts acylation. The Friedel-Crafts acylation substitutes a hydrogen on benzene with a carbonyl group, also called an acyl group. As you can see in the example, the reaction is usually performed with an acyl halide in the presence of a Lewis acid, typically aluminum chloride. Unlike Friedel-Crafts alkylation, the reaction is usually shown with a second aqueous workup step. The second workup step is necessary because the Lewis acid catalyst tends to bind to the oxygen in the product. The water is added to remove the catalyst from the carbonyl oxygen in the product. Just like with the Friedel-Crafts alkylation, the Friedel-Crafts acylation is synthetically very useful because it results in the formation of a carbon-carbon bond. The mechanism of the Friedel-Crafts acylation is pretty straightforward and involves the formation of an acylium ion. The electrophile needed for the EAS portion of the mechanism is prepared in two mechanistic steps. The first step is a simple Lewis acid-base reaction. The acyl halide acts as a Lewis base, donating an electron pair from the halogen into an empty orbital on the metal of the Lewis acid. The carbon-halogen bond in the resulting adduct then cleaves, forming an acylium ion. In the EAS portion of the mechanism, benzene attacks the carbon of the acylium ion, forming a carbon-carbon bond. The resulting resonance-stabilized carbocation intermediate is then deprotonated by a weak base, forming a new pi bond and re-establishing aromaticity. We'll wrap up our look at EAS reactions by exploring a couple of variations on the Friedel-Crafts reactions. We've seen that the Friedel-Crafts alkylation is typically performed with an alkyl halide. However, it's also possible to perform a Friedel-Crafts alkylation with an alcohol or an alkene in the presence of a Bronsted acid catalyst. The first example shows benzene reacting with 2-propanol under acidic conditions. The alkyl group attached to the oxygen in the alcohol replaces one of the hydrogens on the benzene. In the second example, we see benzene reacting with 1-propene under acidic conditions to give the exact same product. The same product is formed because both reactions involve the formation of the exact same carbocation intermediate. You might have seen that alcohols can be protonated under acidic conditions. The resulting alkoxonium ion can then expel water to form a carbocation. You've also seen alkenes react with strong acids to form a carbocation. Think of the first step in the hydrohalogenation or the acid catalyzed hydration reactions. The alkene accepts a proton in order to make the more highly substituted, more stable carbocation. In each case, the carbocation serves as the electrophile in the EAS reaction mechanism. The Friedel-Crafts acylation, which typically involves the reaction of an acyl halide, can also be performed in the presence of an acid anhydride. You can think of an acid anhydride as an oxygen bonded to two carbonyls. As you can see in the example, one of the two carbonyl groups attached to oxygen replaces a hydrogen atom on the benzene. The reaction doesn't require a catalyst, but is typically performed at elevated temperatures.